Okay, so welcome back to this next video in which we are discussing voltage-gated potassium channels. Okay, right, so we're in the process of discussing the generation of an action potential. Right, so we're just in the process of discussing the concept of a chemical synapse. Okay, so we've discussed how this neuron is going to have a huge number of dendritic spines, and these dendritic spines are the sites of connection between this neuron and other neurons. So other neurons are going to have their axon terminals synapsing onto dendritic spines. Okay? So here's one of these axon terminals. Now we're assuming that this is a glutamatergic axon terminal, hence why I've color-coded it red. Okay, so what it will be doing is when action potentials arrive in the axon terminal from the axon, okay, that action potential will cause the release of glutamate into the synaptic cleft. Okay, and the glutamate is then going to act on receptors on the postsynaptic membrane. Okay, so let me put these here. Now, the main receptors for glutamate are ligand-gated ion channels, which, when glutamate binds to them, will open and open up an ion channel down which ions can move. And the main ion which these ligand-gated ion channels for glutamate are permeable to is going to be the sodium ion. So what can then happen is when you open this ligand-gated ion channel where the ligand is glutamate, that's going to allow sodium to move across the cell membrane, and of course sodium's electrochemical gradient favours the movement of sodium in. So what you're going to get is sodium moving into the cell. Now what that's going to do is it's going to contribute to the depolarization of the electrical potential difference across the cell membrane. Okay, and this is probably something I should have mentioned right at the beginning. All cells in your body have an electrical potential difference across the cell membrane, okay, including neurons. Now this is not just a feature of excitable cells, it's all cells, okay. Not all cells are capable of an action potential, that's the definition of excitable cells, but all cells do have a resting electrical potential difference across their cell membrane, okay, and neurons are just the same. So what is this resting electrical potential difference? Well, usually the resting electrical potential difference across a cell membrane is around negative 65 millivolts. So what this means is that the electrical potential in the inside of the cell, okay, in the cytoplasm, so if you go anywhere in the cytoplasm, the electrical potential at any of those points is 65 millivolts lower than the electrical potential of any of the points outside the cell. Okay, so basically if you move across the cell membrane, your electrical potential goes down, and it goes down by 65 millivolts. Right, so when you bring in sodium ions into the cell, the effect on the electrical potential is to make it less negative, because when you bring sodium ions into the cytoplasm of the cell, sodium is going to raise the electrical potential in the cytoplasm of the cell. Okay, in addition, you're moving this sodium from somewhere. Okay, you're moving it from the extracellular fluid, so when you move it out of the extracellular fluid, that's going to decrease the electrical potential of the extracellular fluid. Okay, the reason that sodium increases the electrical potential of an area is because it's a positively charged ion. Okay, so let's draw this on a little diagram like so. Let's let this line here represent the electrical potential extracellularly, which I'll abbreviate to capital E subscripted E. So capital E is for electrical potential, then the subscript E is for extracellularly, okay, and we'll let this line here represent the electrical potential intracellularly, so the electrical potential of any point in the cytoplasm. So previously we had to go down by 65 millivolts when we moved from extracellular to intracellular. But now what I'm saying we're going to do is, because we've moved sodium into the cell, we're going to be raising the electrical potential intracellularly, so maybe it goes up to here, and because we've moved the sodium ions out of the extracellular fluid, we're going to be lowering the electrical potential extracellularly. So now the drop that you're going to go down when you move from extracellular to intracellular, it's going to be smaller. Okay, so the electrical potential difference, or the voltage across the cell membrane, is going to become less negative, basically. Okay, more positive, closer to zero basically, or even going into the positive places where the electrical potential intracellularly will actually be higher than the electrical potential extracellularly. And that's what's known as depolarization of the electrical potential difference across the cell membrane. Okay, right, so when you open ligand-gated ion channels for glutamate, that depolarizes the electrical potential difference across the cell membrane because you are allowing sodium in. GABA does the exact opposite. GABA will open ligand-gated ion channels as well, but those ligand-gated ion channels will be for chloride anions, negatively charged ions, okay? And again, chloride will come into the cell when you open those chloride channels. And the chloride then will decrease the electrical potential intracellularly because it's a negatively charged ion, and because you've moved it out of the extracellular fluid, that will increase the electrical potential extracellularly. So chloride will actually make the electrical potential difference more negative. The amount you'll have to step down will be increased, okay? So it will actually hyperpolarize the electrical potential difference across the cell membrane. Okay, so let's say that suddenly the glutamatergic input to this neuron has become stronger than the GABAergic input. Okay, so the amount of sodium you're letting in now from all these different dendritic spines is going to beat the amount of chloride that you're letting in because of the GABAergic input. Okay, and what happens is all of these sodium currents coming in from the dendritic spines are going to be diffusing into the portion of cytoplasm near the axon hillock here. Okay, so you're going to be getting sodium moving in from all the dendrites, and it's going to be coming to the axon hillock where the action potential can start. Okay, and this is just by random diffusion, okay? The sodium isn't sort of saying, right, we have to head for the axon hillock. It's just some of it will end up going to the axon hillock. Okay, so all of this excitatory input will be contributing to the arrival of sodium in the cytoplasm at the axon hillock. Of course, chloride anions will also be coming here, but let's say that the amount of sodium ions is now much bigger than the amount of chloride anions, and therefore we're going to trigger the axon hillock to fire an action potential. Okay, normally what would happen is the excitatory input will be balanced by the inhibitory input. Okay, so the sodium positively charged ions will be perfectly balanced by the chloride negatively charged ions, and that would not cause the axon hillock to fire an action potential. But now let's say that the sodium current is going to beat the chloride current, so that the axon hillock is now going to fire an action potential. So basically, when more sodium arrives here than chloride, what will happen is that will cause the depolarization of the electrical potential difference across the cell membrane at the axon hillock. Okay, and that then is going to trigger an action potential to begin in this portion of membrane at the axon hillock. So let's go into this in a little bit more detail. So let's say this is the axon hillock cell membrane. Oh, and I'll just move this up a little bit. Right. So I'll highlight it in blue, since I boxed the axon hillock in blue previously. Right, so this portion of membrane and all of the membrane downstream of the axon hillock along the axon is special because it is excitable membrane. It's capable of firing an action potential. Okay, and the reason it's capable of doing that is it's going to have the correct voltage-gated ion channels to do it. Okay, so we now know that what's happening here is we're depolarizing the electrical potential difference across the cell membrane here. Okay, so the voltage across the cell membrane is becoming more positive, it's becoming less negative, because of the bigger sodium current here than chloride current. Okay, so we've tipped that balance, and now it's going to activate an action potential. So let's have a look at how this occurs. Okay, so the first thing that happens is you're going to activate the voltage-gated ion channels. Okay, so I'll draw these here. So we need two types of voltage-gated ion channels when we're going to discuss the action potential. I'm just going to draw them very, very simply at the moment. Okay, just like so. So we'll colour in one in red, this little sort of structure with a pore going down the middle. This is going to represent our voltage-gated sodium channel, so this is our VGNC. And this other one is going to be our voltage-gated potassium channel, our VGKC here. Okay, and I'll colour that in green here. Right, okay, so Basically, when you depolarize the electrical potential difference across the cell membrane up to a certain level, it's going to activate these voltage-gated ion channels, okay? And this special electrical potential difference that you have to depolarize up to in order to open the voltage-gated ion channels is known as the threshold potential, and generally it's around negative 40 millivolts. Okay, so this is called threshold potential. It's the threshold electrical potential difference that you need to depolarize up to in order to activate the opening of the voltage-gated ion channels. Okay, right. So, what then is going to happen is when we depolarize up to threshold potential, if we depolarize up to threshold potential, if the glutamatergic input into the neuron is big enough to overbalance the GABAergic input to the neuron so much that you depolarize the electrical potential difference across the axon-hillock membrane up to around negative 40 millivolts, then what will happen is the axon-hillock will begin firing an action potential, and what's going to happen is the voltage-gated sodium channels and the voltage-gated potassium channels are going to be activated to open. Now, they do not instantly open at the same time. Okay, the voltage-gated sodium channels, once they have been activated to open, they are going to open extremely fast. Okay, the voltage-gated potassium channels, however, they take much longer to open, okay, and this is such an important concept to understand. This is the crux of the action potential. The voltage-gated sodium channels and the voltage-gated potassium channels, they're both activated pretty much at the same point, but these ones open really quickly after being activated, and these take much longer to open. Okay, so let's talk about this. So what's now going to happen is once you get up to negative 40 millivolts, all of the voltage-gated sodium channels in this little portion of membrane here are going to start opening, and they're going to open really quickly. And I want to stress that even though I've just drawn one voltage-gated sodium channel, you know, we're talking about a little section of membrane here. There's going to be loads of voltage-gated sodium channels there, and they're all going to be opening. Okay, so what's going to happen is they're going to all open very quickly, and they're going to make a pore through which sodium can move across the cell membrane. Now, sodium's electrochemical gradient favours its movement inwards. Okay, remember the concentration gradient for sodium across the cell membrane is approximately 145 millimolar sodium concentration extracellularly, and then 12 millimolar sodium intracellularly. So approximately a 12-fold gradient favouring the movement of sodium in. You also have to take into account the fact that the electrical potential difference across the cell membrane is currently around negative 40 millivolts. Okay, that means that the electrical potential intracellularly is 40 millivolts lower than the electrical potential extracellularly. Sodium is a positively charged ion, so it wants to go where the electrical potential is lower, which is the intracellular compartment. So both the electrical gradient and the concentration gradient are saying move in for sodium. So when you open sodium channels in the cell membrane, you're going to get a sodium current coming into the cell. Okay, what is that then going to do to the electrical potential difference across the cell membrane? Well, it's going to depolarize it further, okay, because you are bringing in positively charged ions into the intracellular compartment. Okay, so the electrical potential intracellularly, EI, is going to be going up further, and the electrical potential extracellularly, capital EE, is going to be going down because you're bringing sodium ions out of there. Okay, so if we go back to this picture, this one's going to be plummeting down, okay, the electrical potential extracellularly, and this one's going to be plummeting up, okay, and it will actually get to the point where the electrical potential intracellularly is now higher than the electrical potential extracellularly, so the electrical potential difference will become positive, so it'll be like this, basically. Here is the electrical potential extracellularly, here is the electrical potential intracellularly, and you've now got to move up to get from extracellular to intracellular. Okay, so what people absolutely love to do when they talk about the action potential is plot a graph of this. Okay, so what you plot is the electrical potential difference across the cell membrane. So, we're talking about the electrical potential difference across the axon-hillock cell membrane. Okay, and it would have originally started off at resting membrane potential down here. Then when the glutamatergic input started beating the GABAergic input, okay, and you got this initial sodium current that beat the chloride current coming into the axon hillock cytoplasm, that will cause the depolarization of the electrical potential difference up to this threshold potential of -40. Okay, then what will have happened is the voltage-gated sodium channels and the voltage-gated potassium channels will have been activated to open, but as of yet, the voltage-gated potassium channels haven't actually opened. They're being very slow about it. So initially what happens is the voltage-gated sodium channels open, and they open extremely quickly, and this means that you're going to get depolarization of the electrical potential difference across the cell membrane that's very rapid. Okay, and it goes all the way up to around plus 40 millivolts, okay? So now the electrical potential intracellularly is 40 millivolts higher than the electrical potential extracellularly. Okay, right, then what happens is these voltage-gated sodium channels undergo inactivation, okay? So this phenomenon where even though we're depolarized of the threshold potential, so the voltage is still saying stay open to the voltage-gated sodium channel. Even though that's the case, the voltage-gated sodium channel is going to close, okay? And this phenomenon is known as inactivation. Okay, so the cause of this is not that the voltage-gated sodium channel is going back to the state that it was in before it was even activated. It's going into a different state known as the inactivated state. Okay, and we'll talk about this more for the voltage-gated potassium channel later, but it's a very similar phenomenon for the voltage-gated sodium channel. Okay, so the voltage-gated sodium channels then inactivate and close. Okay, right, so they're no longer letting any more sodium current come into the cell. Then, just as the voltage-gated sodium channels finally close or inactivate, what happens is the voltage-gated potassium channels only just about get round to actually opening. Okay, so they start opening now, even though they were activated to open long ago back here when we reached threshold potential. Okay, so the voltage-gated potassium channels now open and make a channel through which potassium can move. Right, so which way is potassium going to move? So we need to know what the electrochemical gradient for potassium is. So the concentration of potassium extracellularly is around 4 millimolar. The concentration of potassium intracellularly is around 155 millimolar. Okay, so there's around a 40-fold gradient of potassium favouring its movement outward. Okay, so the concentration gradient's pretty clear. We then need to consider the electrical potential difference across the cell membrane. Currently, the electrical potential difference across the cell membrane is plus 40 millivolts, okay, which means that the intracellular compartment's electrical potential is 40 millivolts higher than the extracellular compartment's. Okay, potassium wants to be where the electrical potential is lower because it likes to be, because it's a positive ion, so it wants to be where the electrical potential is lower. Okay, which is currently the extracellular compartment. So initially, both the electrical gradient and the concentration gradient say move out for potassium. So potassium is going to move out. Now that's going to have the exact opposite effect on the electrical potential difference across the cell membrane to moving sodium in. When we moved sodium in, that depolarized the electrical potential, it made it more positive. We're now moving positive charge out, that's going to do the exact opposite. It's going to repolarize the electrical potential difference across the cell membrane. Okay, because what we're going to do now is we're going to lower the electrical potential intracellularly, because we're moving potassium ions, which are positively charged, out of the cell. Okay, so the electrical potential intracellularly is going to go down. And then because we're moving positive charge into the extracellular fluid, that means the electrical potential extracellularly is going to go up. Okay, and that's going to repolarize the electrical potential difference across the cell membrane. So what will start happening is the electrical potential difference will start going down. Okay, and we'll go back into the negative regions. Now then, I have to provide you with another explanation. Okay, because now we're back to the case where the electrical potential difference across the cell membrane is negative, okay, which means that the electrical potential intracellularly is lower than the electrical potential extracellularly. That means that potassium is now going to be wanting to stay in the intracellular compartment because it wants to, remember, be in the place where the electrical potential is lower, which is now the intracellular compartment. So once the electrical potential difference becomes negative again, the electrical gradient is now going to be saying to potassium, stay in the cytoplasm of the cell. However, this concentration gradient of 155 millimolar intracellularly and 4 millimolar extracellularly is still stronger than that electrical gradient, so you still get potassium moving out. It will go down, the potassium current will decrease because now the electrical gradient is opposing the concentration gradient and saying no, stay in. Okay, but it will still have a net movement out. Okay, so this means that the process is going to continue on. Basically, you're going to go down and down and down and down. To add a little bit of extra information to this explanation, you'd actually have to take the electrical potential difference across the cell membrane down to around negative 85 millivolts, okay, where the intracellular electrical potential is 85 millivolts lower than the extracellular electrical potential in order to balance the concentration gradient, i.e. if the electrical potential difference across the cell membrane was negative 85 millivolts, then no potassium would move across the cell membrane. This is strong enough to completely block potassium moving out of the cell because of the concentration gradient. Okay, so provided that we are above negative 85 millivolts, we're not that extreme. Okay, so for instance, we're, even here, we're only at negative 65 millivolts. That is not going to be strong enough to oppose the concentration gradient, and you're always going to have potassium moving out. Okay, so that's the Nernst potential for potassium there. Right, so what will happen is actually it will start to go a little bit hyperpolarized of negative 65 down to around here, and then what will happen is these voltage-gated potassium channels will inactivate as well. Okay, and then what will happen is the voltage-gated potassium channels and the voltage-gated sodium channels, those are now both shut. Okay, so there's no more of these sodium currents or these potassium currents acting anymore. Okay, and then what will happen is the sodium channels and the potassium channels that are leaky in this cell membrane, along with the sodium-potassium ATPase, will just re-establish that incredible equilibrium that gives resting membrane potential. So what will happen is that you'll just gradually go back up to resting membrane potential, because remember, that's the only way you can be at equilibrium. There is that fantastic equilibrium of charge movement across the cell membrane and also ionic movement across the cell membrane that is brought about by the leaky sodium and potassium channels that are in the cell membrane, and also the sodium-potassium pump. Okay, I'm not going to go into that because it's a long explanation, but that's what causes this repolarization, basically. It's just you returning back to that wonderful equilibrium, basically. Okay, right, so that's a reminder then of the action potential. Okay, so we've seen that the voltage-gated potassium channels are going to be activated to open at this threshold potential of around negative 40 millivolts. We want to see why that is, what actually underlies that activation. Okay, we've also seen that the voltage-gated potassium channels will gradually inactivate. Okay, now, even though I said they inactivate down here, in reality that, there's loads of voltage-gated potassium channels here, and many of them will be inactivating all the way along this downstroke of the action potential. They don't all suddenly inactivate at this point. Okay, because you might be wondering, well, we're back right at a negative electrical potential difference across the cell membrane here. Okay, why don't they just close? Okay, because the voltage stimulus is gone now. Okay, some of them that have made it all this way will just close. Okay, but many of them that are closing on the way down this slope of the action potential and are closing before you get down to before you get down to hyperpolarized of the threshold potential here, those will be closing because of inactivation, and we want to see what underlies that. Okay, right. So, that's the action potential then. Now let's move on to discussing the structure of the voltage-gated potassium channel. Right, so the first picture that I'm going to draw you of the voltage-gated potassium channel is going to be completely oversimplified. Okay, so oversimplified that it's a little bit incorrect, okay? But it will help to get one important concept out of the way first, and then we will modify it to make it more correct. Okay, right. So the first picture I'm going to draw of a voltage-gated potassium channel looks like so. Okay, so now I'm promoting the cell membrane to being represented by two parallel lines rather than just one parallel line. Okay, remember the cell membrane is a phospholipid bilayer, so these two lines represent the inner leaflet of the phospholipid bilayer and the outer leaflet of the phospholipid bilayer respectively. Okay, so then we'll have the voltage-gated potassium channel sitting in the cell membrane like so. So it's an integral membrane protein. Okay, so here it is. So initially I'm just going to represent it as a great cylinder like so. And here is the ion permeation pore down the middle. Okay, now in the closed state that pore will be narrowed, okay, and in the open state it will be much wider so that potassium ions can actually move through it. Okay, so what's the important concept that I want to get across with this picture? Well, it's the concept that actually the voltage-gated potassium channels are not just one protein. Okay, in fact, you have to put multiple proteins joined together to make a voltage-gated potassium channel. Okay, so you take 4 separate polypeptides and you join them together to make a tetramer, and that is your voltage-gated potassium channel. So it's not just a single protein. You have to join multiple proteins together, specifically 4 proteins together, to make the fundamental pore-forming unit of the voltage-gated potassium channel. Now, as we'll see later on, you can actually add additional polypeptides onto this complex to make it even more complicated, but the most basic voltage-gated potassium channel that you could build just has these 4 basic subunits. The other subunits that you can add on are what are known as auxiliary or accessory subunits, okay? They're not fundamentally necessary to build a functional voltage-gated potassium channel. However, these 4 fundamental subunits that I've shown here, these are the 4 fundamental subunits that are needed to build the pore-forming unit of the voltage-gated potassium channel. Okay, right. So that's what this picture is trying to communicate, that there are 4 separate subunits that make up the main portion of the voltage-gated potassium channel. So these main subunits are known as alpha subunits of voltage-gated potassium channels. We're also going to see beta subunits later on, but they're accessory subunits. So you take 4 alpha subunits, bind them together into a tetramer like so. Each one of them makes up a quarter of it, and then you've got your full voltage-gated potassium channel. Right, so now what I want to do is pull out one of these individual alpha subunits of the voltage-gated potassium channel, and that is an individual polypeptide, and I want to look at its structure. I want to look at its membrane-spanning topology and certain important features about it. Okay, right, so let me do this now, and I'll do this here. So here again is the cell membrane, and I should just make it crystal clear. The top is always going to be the extracellular fluid side, okay, and the bottom is going to be the cytoplasm, okay, of the cell and these are the 2 sides of the cell membrane, clearly. Right, so that same convention we are using in this bit of membrane here. Okay, the top is the extracellular fluid, the bottom is the cytoplasm. Okay, and I apologise, it's a little bit cramped, but we'll make do. Right, so we're now drawing an individual alpha subunit of a voltage-gated potassium channel. Now this is an individual polypeptide. So here is the amino terminus of this polypeptide. Then following the amino terminus you have an important domain which I'm going to talk about in a moment, okay, known as the T1 domain. Okay, sometimes in full this will be called the T1 tetramerization domain. Okay, which tells you what it's important for. It's important in tetramerizing alpha subunits together. Okay, so it's important in holding together the 4 separate alpha subunits. So I'll colour in the T1 tetramerization domain in green here. So this is T1 tetramerization domain. Right, then after the T1 tetramerization domain you have the first membrane-spanning alpha helix. Okay, here. And I've drawn this as a straight line because it looks clearer if you draw it as a straight line, but in reality it will be an alpha helix, so it'll be a spring-shaped structure. Okay, right, so that's our first membrane-spanning alpha helix. Then the polypeptide is going to turn around and it's going to come back in. So second membrane-spanning alpha helix, third membrane-spanning alpha helix, fourth. Then you have a special portion in between the fourth and the fifth on the cytoplasmic side, which we'll come back to. This is actually an extremely important part of this structure. Okay, then we've got the fifth membrane-spanning alpha helix, a structure that is a re-entrant loop, so it goes into the membrane, doesn't quite make it all the way through, and then turns back and comes back out. Okay, and then our final sixth membrane-spanning alpha helix here, and then we'll finish with the C-terminus. So what I want to do is colour in pink membrane-spanning alpha helices firstly. Okay, so we've got six membrane-spanning alpha helices here. 1, 2, 3, 4, 5, 6. Okay, right, and these have all got special names. So the first one here is what's known as S1. Okay, the second one is then known as S2. The third one is S3, the fourth one is S4, the fifth one is S5, and the sixth one is S6. So these are labelled S1 through S6. Okay, and to add a few more labels on here, you then have this re-entrant loop here between S5 and S6, and this is what's known as the P loop. Okay, then we have this special section in between S4 and S5, and by the way, we'll come back to what all of these sections do later on. Okay, well, at the moment we're just labelling them up. Okay, so this section between S4 and S5, this is known as the S4 S5 linker, and this is important in the gating mechanism. Okay, right, what I want to add on is a few more important alpha helices, and I'm going to colour these in a similar colour. I'll colour them in red. So a few more alpha helices that are not membrane-spanning alpha helices, but are still important alpha helices, is you have an alpha helix in the S4 S5 linker there, and also an alpha helix on the first portion of the P loop there. Okay, and that alpha helix on the portion of the P loop here is known as the P helix. Okay, so this is called the P helix, and then the helix in the S4 S5 linker is then just called the S4 S5 helix. Okay, so we will come back to the function of the P loop and the S4 S5 linker in a moment. Right. The other thing that I want to say, just before we now go on to the structure of the whole tetramer, because I'm going to show you how these things fit into the entire tetramer in just a moment, and I'm going to draw a more accurate picture. The thing that I just want to say before we do that is that you can see that it's almost divided into these two separate portions. There is this first portion, which has the first four membrane-spanning alpha helices, S1 to S4, okay? And then there is this second portion here, which contains S5, the P loop, and then S6. Okay, and these two portions actually are physically separated, firstly in the actual tetramer, as we'll see in just a moment, and they're also completely distinct in what their function is. Okay, so the S1, S4 section is what's known as the voltage sensing domain. Okay, this portion is important in reacting to changes in the electrical potential difference across the cell membrane. Particularly the S4 helix is incredibly important for sensing the electrical potential difference across the cell membrane and reacting to it. Okay, then we've also got this other section, which is S5, then the P loop, and then S6. And this portion is the portion that actually forms the pore. So this is what's known as the pore forming domain. Okay, and as we'll see, this is the portion that actually lines the pore of the voltage-gated potassium channel. Okay, so what we're now going to do is we're going to redraw out the voltage-gated potassium channel tetramer, and we're going to draw it more accurately. We're going to actually show what it actually looks like, rather than this very nice, simple picture here. Okay, because in reality, it's quite a bit more complicated. Okay, so what I'm going to do then is I'm going to draw what the voltage-gated potassium channel looks like from above, okay, because it's far easier drawing it just as a two-dimensional structure from above than it is drawing a three-dimensional picture like this. Okay, it was easy to draw a three-dimensional picture when all I was drawing was so simple as this, but now we're going to draw it from above and we're going to see what it looks like in reality. Okay, and it's too difficult for me to draw it in 3D. It just ends up looking really awful, basically. So I'm going to draw it from above rather than from this three-dimensional angle as we've been looking previously. Okay, right, so before I do that, what I just want to draw out is my single subunit structure first, okay? And I want to color code each of the important portions, okay? So that I can then color them in where they are on the picture when I draw it. Okay, so here we go, there's S1 to S4, here's the S4, S5 linker, here is the P-loop, S6, and then all we need to add on is the tetramerization domain, although I'm not going to show you that until the next picture, okay, and then we'll have the C-terminus here. So let's color code portions then. So firstly we'll color in the S1 helix in blue, then we'll have S2 in red here. Okay, and because of lack of colours, we're going to have to use yellow for S3, which is an awful choice, but never mind. Then S4 we'll have in orange. Okay, we'll then have the S4, S5 linker in vivid purple. Okay, we'll have S5 in green. Okay, we'll then do the P-loop again in vivid purple, again because of the lack of colours. Okay, and then finally we'll have S6 in turquoise here. Right, okay, so now let's show the voltage-gated potassium channel from the top, and I will show you where each of these structures that we have now color-coded is on the picture. Okay, so basically, if you draw a more accurate picture of what the voltage-gated potassium channel looks like from the top, it does not look like a simple circle as my previous picture would have implied. Okay, so my previous picture would have implied that it would just look something like this. Well, this is what part of the structure looks like. This is what the pore-forming domains form. Okay, but we now need to add on the places where the voltage-sensing domains are. And basically, the voltage-sensing domains are stuck off from the sides, like so. Okay, but it's slightly more complicated than you'd think. Okay, there's another subtlety here, I'm afraid. Because you're probably thinking at the moment, great, so the pore-forming domain sits here, okay, and you've got 4 of them, that's good, and then the voltage-sensing domain will just sit behind it, like here. Okay, but it's not quite that simple, because this voltage-sensing domain here is not the voltage-sensing domain of the pore-forming domain here. Instead, it's the voltage-sensing domain of this pore-forming domain here, and I'm sorry, my hand's in the way. It's the voltage-sensing domain of this pore-forming domain here. So this one is paired with this one. This is the same subunit here, this one and this one. This one here is paired with this one here. This one here is paired with this one here. This one here is paired with this one here. So that's a subtlety that makes this more difficult to understand. Okay, so what I now want to do then is put one of these subunits into this picture and show you where each of the portions is. So we'll start with the pore-forming domain. We'll start from the end, basically. Okay, so we will show it for this subunit here. So here's the pore-forming domain, and then the voltage-sensing domain will be this portion here. Okay, so firstly, the portion that actually is going to be lining the pore, at least from the extracellular side, is actually going to be the P-loop. Okay, so I'm going to colour that in pink here. So that's that P-loop there, which will actually be lining the pore. Okay, then behind the P-loop, what you're going to have is the S6 helix. Okay, here in blue. Okay, whoops. Then behind the S6 helix, in this sort of position here, you're then going to have the S5 helix. Okay, so this is the S5. So you've got S5, then that will turn into the P-loop, and then after the P-loop you've got S4. Okay, and they're positioned like so. Okay, then let's put in the voltage sensing domain, and that's going to be this portion over here. So firstly we'll start off with the S4 helix in orange here, Okay, and the S4 helix and the S5 helix will be linked together by an S4, S5 linker, which will be on the cytoplasmic side. So we wouldn't be able to see this really because we're looking from the extracellular side. Okay, but I'm going to put it in there for conceptual reasons. Okay, but we wouldn't be able to see that because we are looking from the extracellular side, and the S4, S5 linker should really be on the cytoplasmic side. Okay, so this is the S4, S5 linker. Okay, right. Then let's put in S3. S3 will sit here alongside S4. Okay, shown in yellow. Then let's put in S2. S2 will sit behind S3. What colour is S2 in? Red. Okay, so here then is S2. And then finally we'll have in S1, and S1 will be sitting in that final position there. And we'll have oh dear, sorry, I've miscoloured this in. I've coloured S6 in blue when in fact it was supposed to be in turquoise. I apologise for that. They look similar under this light. Okay, so this should have been in turquoise. I'll try and rectify that. There we go. Okay, so this is the S6 helix. They're on the opposite side, so I think it hopefully should have avoided any confusion there. Right, okay, so there's a single subunit. Okay, so just to make it crystal clear, what I'm going to do is put another one in now. Okay, so let's put in this one here now, okay, just to make this concept completely clear, because it's not the easiest concept to understand in the world. Okay, so let's put another one of these subunits, another one of these alpha subunits in. So here's the P loop, then we'll have the S6 helix sitting behind that, the S5 helix behind that. Okay, then we've got the S4 helix here, the S3 helix here, the S2 helix here, and the S1 helix here. Okay, so let's colour everything in. So here's the P loop lining the pore from the extracellular side in pink here. Okay, then you've got the S6 helix sitting behind that. And I've coloured it in blue again, damn. Sorry about that. It should have been in turquoise. Right. Then we've got the S5 helix behind that in green here, and I'll just straighten up the piece of paper. Right, and then we've got the S4, S5 linker between S5 and S4 there. Then in orange we've got S4 here. Okay, sitting alongside it we've got S3 in yellow. Behind S3 you've then got S2 in red. And then in the final remaining place you've got S1 here in blue. Right, okay, so that is the positions of the alpha helices then of this single voltage gated potassium channel subunits. Okay, and of course you could continue this on. You could put another one here and here, and then the final one here and here, and that would make you then the voltage gated potassium channel tetramer. Okay, right, so that's the more correct structure of a voltage gated potassium channel. This is the very simplified picture where really all that we're truthfully showing here is the pore forming domains. We should have the voltage sensing domains sitting peripheral to that. Okay, right. So now what I want to talk about is what is holding these four subunits together, these four alpha subunits together. I want to talk about the T1 tetramerization domain. And even though I have just condemned my previous picture, which was oversimplified, I am now going to go back to using that previous picture to show the tetramerization domains tetramerize together. Okay, so I'm going to go back to representing my voltage-gated potassium channel simply as a cylinder like so, okay, with a pore down the middle. Okay, so truthfully, all this is showing is really the pore-forming domains here. Okay, tetramerized together. Okay, I've missed out the voltage-forming domains which should be sitting peripheral to it. I might have a go at drawing one in. There we go, there's one, there's another one. I won't try and put them in front of, in fact I can't resist the temptation now. Okay, the final two should be here, and now you realise why I didn't plan to draw this in, because it looks far more complicated than it needs to. Okay, but that's what it would look like if you tried to draw it from the side like that. Okay, so I have tried to draw it there. Okay, so the aim, however, of this picture was not to try and show it from the side. What the aim of this was to show the tetramerization domains tetramerized. Okay, so basically, let's just remember where the tetramerization domain is. So here is the tetramerization domain prior to the S1 membrane spanning alpha helix. So what you'll have is from all 4 of these alpha subunits, you'll have a tetramerization domain dangling down into the cytoplasm. And what ends up happening is these 4 tetramerization domains, as the name suggests, they tetramerize. Okay, so I'll show this here. So this is a tetramer of these tetramerization domains. Okay, so here's one, here's another one, which will be the subunit back here, and this one here will be corresponding to this subunit back here. Okay, so if I color code this up a little bit, let's try and show one subunit here. So this one in red, here is its pore forming domain, of course, here. Okay, and here is its tetramerization domain. Okay, so that's the red subunit. Okay, let's try and show another one. We'll have this blue one here. Here's the voltage sensing domain. Here's the pore forming domain. Okay, and then here is its tetramerization domain. So remember, of course, the tetramerization domain is upstream of S1, which is part of the voltage sensing domain. So it will be dangling down below the voltage sensing domain rather than below the pore forming domain. Okay, and let's just show one more maybe. Okay, so here in turquoise, here is that pore forming domain, here's the voltage sensing domain, and there's its tetramerization domain. And in fact, I might as well finish it off now. Here is the final one in orange, here is its voltage sensing domain, here is its pore forming domain, here is its tetramerization domain. So these tetramerization domains tetramerize below the voltage gated potassium channel, basically. Okay, and that's believed to underlie how this remains held together, that the tetramerization domains are tetramerized together in this way. Okay, right. So that's the structure then of a voltage-gated potassium channel. Okay, we're going to have a break there, and in the next video what I will talk about is the diversity of voltage-gated potassium channels. I will talk about the fact that there are many different alpha subunits of voltage-gated potassium channels. I will also talk about how they can be built, okay, so how you can build both homotetramers and heterotetramers, and then we'll talk about the accessory beta subunits.